This is a presentation about how objects fall when the only force is gravity. I'm going to discuss how the velocity of an object changes when it is in the state of free fall, and I will go over the shapes of the velocity versus time and displacement versus time plots for free fall. An object is thrown up at a velocity of 30 meters per second. How long will it take to hit the ground? When learning about free fall, it's convenient to round off the acceleration due to gravity, which is negative 9.8 meters per second squared, to negative 10 meters per second squared. If we make the acceleration due to gravity negative 10 meters per second squared, this means that the velocity of the object will decrease by 10 meters per second each second on the way up. If the object is thrown up at 30 meters per second and the acceleration due to gravity decreases the velocity by 10 meters per second each second, it will take 3 seconds for the object to reach the peak. When it leaves the peak, gravity will add negative 10 meters per second each second, and it will take 3 seconds to return to the object's original position. When the object returns to the place where it was initially thrown, it returns to its initial speed of 30 meters per second, but since it's moving downward, its velocity is now negative 30 meters per second. Here is the velocity versus time plot of the data you just looked at. Notice that the slope is constant because the acceleration due to gravity is constant. The object always decreases by 10 meters per second each second. The slope of this plot is negative 10 meters per second squared. The object begins with a velocity of 30 meters per second, and in 3 seconds the object reaches the peak. After the object reaches the peak, it returns to its starting point with a velocity of negative 30 meters per second. Once again, we're going to round off gravity to negative 10 meters per second squared to make the math a little bit easier for us. The object starts off at 40 meters per second and loses 10 meters per second each second. When it reaches the peak, its velocity is 0 and it heads down in the negative direction. Each second the ball gains negative 10 meters per second, and when it returns to the start, it has the same speed it had when it was first thrown. The only difference is that the velocity is negative at the end because the ball's direction is now down. The acceleration due to gravity is constant near the surface of any planet or the moon, and this is because the force of gravity is essentially constant near the surface of any planet or the moon. Near the surface of any planet or moon, objects will fall with a constant acceleration. The velocity versus time plot for free fall has a constant slope because the acceleration due to gravity is constant. Which line, the blue or green, could represent the slope of an object falling on Jupiter, and which would represent an object falling on the moon? Since the more massive body Jupiter has a much greater acceleration due to gravity, the blue line could represent the velocity versus time plot for free fall on this planet. Since the acceleration due to gravity is constant, the displacement versus time plot for free fall has the following shape. The acceleration is constant when the velocity of the object increases by the same amount each second. Since the slope of this plot increases smoothly, we know that the velocity also increases smoothly. A ball is thrown upward. What is the acceleration due to gravity at the peak? This is actually a trick question. It's a common trick question because the velocity of the ball is 0 at the peak, but the acceleration due to gravity, as long as that object's in the air, is always negative 9.8 meters per second squared. I'm going to end this presentation with another demonstration of how mass has no effect on free fall when air friction is not a factor. A piece of paper falls differently than a textbook because the paper has a large surface area and a small mass. When the paper is crumbled, friction is reduced significantly, and we get a very different result. In this presentation, you learned that when air friction is insignificant, all masses will accelerate at a constant rate of negative 9.8 meters per second squared. An object always has a velocity of 0 meters per second when it reaches the peak, and the time it takes for an object to reach the peak is equal to the time it takes to return to the original position. Furthermore, the plot of a v versus t plot for an object in freefall has a constant slope, and a d versus t plot has a smoothly increasing slope. This is the end of my presentation on freefall.